So my talk's about monogamy, non-locality, and also macroscopic averages, locality of macroscopic averages. So to give a quick overview, so this was based in two papers. So the idea is work came from two papers, one by Macroscopic and Bruckner, where they derived the monogamy of violation of Bell inequalities from the low signaling condition above. So without assuming quantum mechanics, but just their signaling. So I'll explain, if you don't know what these things are, then in a minute we'll do it. And another paper by Ramanath and other people has considered some sort of macroscopic correlations arising in many being models or big microscopic models, and they consider average macroscopic correlations. And they show that these things are local when the microscopic models are quantum mechanical. So we'll consider, so our work sort of is part of the general framework of Abramsky-Brandenburger, so we use the sheet theoretic framework, and we use these to sort of do a structural analysis of both these results, and we actually managed to get a generalization of these results. So the first one, we generalized the bipartite inequalities to multipartite inequalities. The second one we showed is true not only for quantum mechanical models, but also for any Euclidean models. And we also showed that the two things are basically the same statement, just interpreted in different ways. And more important than generalizing them, we sort of show the structural connection between them, the structural explanation, which is related to a theorem by Abramsky, an old classical mathematical theorem, game theory actually. So in these talk we'll mainly consider just some illustrative example with going into details of general arguments. So, okay, so monogamy and non-locality. So you're familiar with the usual setup where you have Alice and Bob. Each of them can choose between doing one of the two measurement settings. So Alice can choose between measuring A1 and A2, Bob between measuring B1 and B2. And they get some probabilities of getting a certain outcomes, given that it shows certain measurements, AI, BJ, so usually represented on the table. So typically we use Bell inequalities so a violation of Bell inequalities we witness that there's some non-locality in these correlations. So this is a typical example of the Bell model, a typical example of violation of Bell inequality. So the point about monogamy is that if we take a tripartite scenario, so we have Alice, we have Bob, we have Charlie. Again, each of them has two measurement settings. And then an empirical model would be a set of no signaling probabilities of these four. So for each choice of measurement for Alice, Bob, and Charlie. And we can consider the subsystem composed of Alice and Bob alone, which is given by mathemization, quantum mechanics, which is the partial trace. And we can do this because of no signaling. These sort of formula here is independent of the choice of measurement for Charlie. And similarly, we can consider the partial trace or the marginalization, get the subsystem consisting of Alice and Charlie alone. So given any bipartite Bell inequality, we could consider, so we have the subsystem of Alice and Bob, we have the subsystem of Alice and Charlie, and we consider the violations of Bell inequalities, of these Bell inequality, by each of these two subsystems separately. And it turns out that we can violate, so these inequality might be violated, but if so, then this one is not violated. And similarly the other way around. So in fact, there's a trade-off between the violations of these two Bell inequalities. And what happens is that the added inequality, so if you add the two inequalities, it's actually satisfied always. So this is true not only in quantum mechanics, but also in signaling that was proven by this result by Macroscopic. So by the way, if there's any questions at any point, please interrupt. If anything's not clear. Okay, so this is the idea of what is monogamy of non-locality for the simplest scenario where it arises. So now we consider this macroscopic average behavior and try to explain what it is that they mean by that. And so we can think of a microscopic measurement, so we can think of a dicatonic measurement with two possible outcomes. So we can think that we have a single particle that is subject to some interaction A, this is our measurement, and then after being subject to this interaction, the particle will hit one of two detectors, which will be correspond to the outcome 0 or the outcome 1. And this interaction is probabilistic, so if we repeat this measurement many times, what we get are some probabilities. So the probability of getting each of the outcomes for the measurement, that's how we've noted. So now we consider, so instead of a single particle, we consider a beam of n particles. And each of these particles might be differently prepared. And instead of a beam, so you can think of beam photons, you can think of a region of some sort of ferromagnetic material, for example. And so the idea is that we subject each particle to the interaction, to the same interaction, A. So in the case of this ferromagnetic material, these would be, for example, doing magnetization measurements in a certain direction, which corresponds to doing spin measurements to each of the particles. But so you consider the beam of particles as goes through the same interaction, and we'll be dividing into two smaller beams, and each of these smaller beams will be one of the detector, or outcome 1 or for outcome 0. So the outcome of these macroscopic measurements would then be represented by the intensity of the resulting beams. So it's a number between 0 and 1, which represents a proportion of particles that meet the detector corresponding to outcome 1. Okay, and so in this talk, like Ramanathan is in their paper, we're only interested in the mean or expected value of these intensities. So each time you do the same preparation of the beam, and you do the macroscopic measurement, you can get slightly different values for the intensities. So you can think of doing this magnetization measurement, and you get slightly different values around the mean value. And we're only interested in this mean or expected value. We're not interested in these fluctuations for probably this talk. So a way to interpret this mean value, so you can think of it as the average behavior among the particles in the beams or the particles in a region. So if we would randomly select one of the particles in the beam and do the macroscopic measurements on these particles, then we'd get outcome 1 with a probability IA, which is the size of these beams. So if EI are the probabilities for each of the particle I, so I ranging from the 1 to n, which is all the particles in the beam. And as I said, they're different to prepare, so you can have different probabilities of having outcome 1. Then the mean value of the intensity is basically given as the average of these probabilities. And in a way, this situation is analogous to physical mechanics. We have a macro state that arises with an averaging over a large number of microstates, and each microstate can give you the same macrostate. So different microstates can give you the same macros. So in our case, we consider multipartite macroscopic measurements. So we have several macroscopic sites, which consist of a large number of microscopic sites for a large number of particles. So you can think of a beam of particles being sent to each of these macroscopic sites, or you can think of several regions of a ferromagnetic material, and you're doing separate measurements of each of these regions. And so at each of these macro sites, you have a number of measurement settings that you can choose to do a different number of macroscopic measurements. And so we obtain this sort of an average macroscopic Bell experiment. So we consider the mean values of these macroscopic intensities we get from doing these measurements. And these will give us a sort of a model, so a multipartite model, which is sort of representing the average behavior. So if we choose, randomly choose a tuple of particles, one from each of these beams of particles, presenting to each macroscopic site, then, so randomly choose that, and the behavior of these randomly chosen one is what's indicated by the intensities that we get from doing macroscopic measurements. And we'll show, so Ramanathan and all show this for quantum mechanical models, but we'll show that as long as there are enough particles or microscopic sites composing each macroscopic site, then the average macroscopic behavior we get in this way is local, no matter which low signaling empirical model is actually describing the underlying microscopic correlations. So not just quantum mechanical models, but in general, any low signaling models without this problem. So we'll consider again the tripartite scenario, and we're considering, so this might look a bit weird, but we're just considering this because it's the the biggest thing we can visualize and do some nice drawings with. So the idea here, so we consider again Alice, Bob, and Charlie, and each of them has two possible measurements. But now we'll interpret Bob and Charlie as being part of the same beam, so part of the same macroscopic size. So it's kind of a macroscopic side that has only two particles. This one has only one particle. You can think they're more of them. Just considering these two, so it's easy to visualize. Anyway, so we regard the sides B and C as forming one macroscopic side N, and the side A is forming another macroscopic side. And in order to be lumped together, so to be considered the same part of the same macroscopic side, they have to be symmetric or of the same type. So we have some sort of symmetry that identifies and says, well, the measurement B1 and C1 are basically the same measurement, like so it's two different particles, and the same with B2 and C2. So you can think of spin measurements in the same direction, and then the resulting measurement on the macroscopic side is M1 would be sort of the magnetization measurement corresponding to these two spin measurements. Okay, so given any empirical model on the original tripartite, so the microscopic system, then the macroscopic average behavior would be a bipartite model, so only on the macro sides, which are A and N, which is given by the following average of probabilities of the partial models. So you get the probability of getting outcome, or sorry, anyway, so the probability of getting outcome xy for the measurements AI and J is given as the average of the probabilities of doing that with BJ or CJ. So you can see this is sort of the average of behavior randomly choosing between considering Bob or considering Charlie, so randomly choosing one of those. So for example, if you have the W state, design the next measurements, this is sort of the probability table. So you think of all these numbers divided by 24, but at each row sums to 1. So for example, if you do measurements A1, B1, and C1, you get outcome 100 with probability of 124. So if you consider the partial models consisting of Alice and Bob alone, or Alice and Charlie alone, they actually happen to be the same. So the Macron model is also the same as this one, and this happens to be a local model. So another example is this one, which is non-quantum realizable, but it's still no signaling. And actually, if you consider the partial model consisting of Alice and Bob, in fact it's maximally non-local, but the one consisting of Alice and Charlie is local. And when you do the average between them, which corresponds to this macroscopic average behavior model, it actually turns out to be local as well. So we'll see this is not just a particular problem with these examples. So, okay. So you probably noticed these already. There's a simple observation that connects this monogamy and these macroscopic averages. So still in this tripartite example. So let's think of any bipartite Bell inequality. So, like the ones we've thinking before. So this is given by some coefficients, and the bounds are. So, okay, so now we think, so you look at whether this Bell inequality is satisfied by this model consisting of A and N, the macro size. So this is equal to that thing, so you expand it to coefficients and probabilities. Then you substitute the definition of these macroscopic probabilities, macroscopic average probabilities by the Fourier with that. So then you get the following just with some triple manipulation. So you see that this thing is equivalent to, oh, this should be 2R here. So this is the monogamy relation that we were thinking about before. So there should be a 2R in this last equation. So the average model, the average macroscopic model consisting of A and N will satisfy the inequality, this Bell inequality, if and only if in the microscopic model Alice is monogamous with respect to violating this inequality with Bob and Charlie. So we have this monogamy relation being satisfied if and only if in the macroscopic model the Bell inequality is satisfied. So it is a very simple observation that connects to themes two examples we just considered before, we noticed that the average models we got were local. So equivalent, we could say that the example satisfied monogamy relations for any Bell inequality. So this is true for all those single empirical models on the tripartite scenario and concentration, which has two measurement settings inside. So it's nothing particular about the two models that I chose. And so we'll give a structural explanation for why this is the case. And this depends on Barbosa's theory. So first, let me just give you a slight intro where I'll present Barbosa's theory. And it's Abramsky-Brandenburger framework. So I'll give you a very short version of this. It's just a two-slide version of the important parts. So in this framework, measurement scenarios represented by a finite set of measurements, x, and a cover, x, or an abstract simplification complex on x. This is two equivalent ways of looking at it, which indicates the compatibility of measurements. So for example, a bipartite measurement would be represented by this simplification complex. So we have A1 and A2 the measurements for Alice, B1 and B2 the measurements for Bob, and we can do A1 and B2, or we can do B2 with A2, we can do A2 with B1, or A1 with B1, with all the foundations there. And the tripartite one, for example, would be represented by this complex, where I'm considering a whole of the tetrahedron. So we have all the triangles consisting of one A measurement, one B measurement, and one C measurement. And this sort of framework it's not only applicable to Bell type scenarios like these ones, but also to Cauchy-Specker configurations and other sort of general contextuality scenarios. And so in this framework, a no signaling empirical model is represented by a family of probability distributions on the output of measurements in each context. So a context is sort of a set of compatible measurements, and for each of these contexts you get a probability distribution on possible outcomes. So these things are sort of the rows of the table we were considering just before. And then we have the compatibility conditions. So when we have two contexts that have an intersection, then the marginals must be the same. So this is just, in the case of multipartite scenarios that we're considering, this is just no signaling. And then an empirical model is local or non-contextual, in the sense of Bell's theory, like it makes a local and non-contextual hidden variable explanation. But this is true even only if there exists a global distribution on all the measurements at the same time that marginalizes to all these distributions for each measurement context. So we're looking for a global distribution on the outcomes of all the measurements. Okay, so Barbosa's theorem, which is sort of arose first in the context of game theory, so quite unrelated to this, solves the following problem. So for each measurement compatibility structures, so for each scenarios, simplification complexes and covers, is it so that any no signaling empirical model, so any empirical model you define in this scenario, will have a global extension, so will be local or non-contextual. And Barbosa derived the necessary and sufficient condition for these things to be the case. Now he sets out to be a well-known and well-studied notion in database theory, relational database theory, you should know as asynchronicity. So the idea behind this, I'll be very quick with it, is that you find this notion of rank reduction step. So if you have a measurement context, then you have a measurement, so in this case you have measurement A that belongs to only one maximal context, then you can remove these measurements. So you can go these scenarios to that one, reduce these ones to that one. And the cover is considered to be acyclic when it's rank reducible to the empty cover. So you can remove every measurement one at a time in this fashion. First we remove A, then we note E belongs to only one maximal context, namely CDE. We can remove that. We get B, and C. So now C belongs to one maximal context. We can remove D belongs to one maximal context, etc. And we get the empty cover. And so the theorem by Barbosa basically says, so here I'm rephrasing it in our terms, but it basically says that all empirical models on a certain measurement scenario are extendable or are local or non-contextual. measurement scenario is a cyclic. So the idea, very quickly, the idea is if you have such a reduction to everything, you can sort of construct the probability distribution one step at a time by doing some sort of gluing of probability distributions. So it's a notion that generalizes the natural joint of databases. It's defined exactly. So we don't have time to see that in much detail. But then the idea, if it's not a cyclic, then the graph reduction will fail at some point, and there will be a cycle. I mean, cycles are not always like that. There's some sort of cycle. And when there is a cycle, you can build something that's like positive correlation between all the measurements, and then in the last one, probably an anti-correlation. So you get something that's clearly not local. So, okay, so now a structural explanation for the things we're considering. So we go back to our tripartite model, Alice, Bob, and Charlie. So now this is represented by this implicit complex, a hollow tetrahedron, or two hollow tetrahedrons related together. So, sorry, it's a hollow octahedron. And here you can see, as a submodel, the Alice and Bob model. I think there is marked there. And the Alice and Charlie model. And the idea is that we're going to identify Bob and Charlie. And so these orange lines are showing the identification. And we're going to take the quotient Shapiro complex under this identification. So the idea is that we'll remove the things that don't not important, and then we sort of collapse the two things together. And we get M1 and M2. So M1 comes from E1 and C1, and M2 will come from E2 and C2. We just collapse these two things together. And you'll notice that the resulting thing is not a simple bipartite scenario, which would be just a square, but it actually composed of these two triangles. So it has more compatibility than a normal bipartite scenario. And so in particular, it's a cyclic, so you can remove A1, and get just a triangle that you can remove in any order you want. That reduces to the empty complex. So in particular, it satisfies this property that any measurement scenario defined on it is local. And so this means that it doesn't matter. So whatever microscopic model on the tripartite scenario we started from, as long as it's no signaling, then the average macroscopic correlations on Alice, on A and M, on the macroscopic size A and M, will be local, because they'll actually be defined on this Shapiro complex. And in particular, they'll satisfy any Bell inequality, and therefore the original tripartite model will satisfy the monogamy relation for any Bell inequality. So this is just the case of the tripartite scenario and the usual monogamy relations. So in fact, you can say something about general multipartite scenarios. So I'll quickly summarize these results. So if you consider n macroscopic sites, A, B, C, etc., and you consider ki measurement settings at the site height, at each site you can choose a number of measurement settings you have. And then at each site, each of these macroscopic sites, we consider that we take Ri copies of each site, or so using sort of the monogamy interpretation. If you're thinking about this macroscopic average, then you think of Ri macroscopic sites or Ri particles that constitute its macroscopic site. So I denoted by A1 to Ri, these upper indices, each of these copies. Then we have the measurement settings at A upper index N. I denoted by this A1 to AKA with the upper index N. So, okay, so we denote these things. So this such a general multipartite scenario is sort of described by the number of macroscopic sites N, a number of Ki of measurement settings for each of the sites, and a number of Ri of copies or microscopic sites composing each of the microscopic sites. And then we have some sort of symmetry that identifies the microscopic sites that correspond to the same macroscopic site. So we'll identify all these A1 to ARI, B1 to BRI, etc. And we'll take quotient of this implicit complex under this symmetry. And this turns out that we have the following results. So the quotient of this measurement scenario by the symmetry cyclic if and only if one of these two things holds. So each site has at least as many microscopic sites or copies as it has measurement settings. So for each of the macroscopic sites I, we have KI, the number of measurement settings, smaller than RI, the number of microscopic sites composing the site. Or is that a similar but that is strange different condition where in one of the sites we have only one copy and in all the others we say we have the same condition. And the interpretation of these things, so the first one lends itself to the interpretation in terms of macroscopic averages. So as long as you have enough particles in each of these macroscopic sites, as long as you have at least as many particles as you have measurement settings, then this macroscopic average behavior, this macroscopic average correlation we're talking about will be local, independently of which no signaling theory describes the microscopic correlations. Whereas the second one sort of lends itself to the interpretation in terms of monogamy, where we have one site Alice, and we have a number of copies of Bob's, a number of copies of Charlie's, etc. And we have some sort of multipartite Bell inequality with n parties, and if we sum all these Bell inequalities, then sort of the added inequality will be satisfied. So if we sum it for all the copies of Bob, Charlie, etc., so the Bell inequalities with Alice, then this thing, so the added inequality will be satisfied. So, summary. So we have some sort of symmetry on the measurement scenario that identifies certain measurements that have to be lumped together, and certain sites are to be considered as the same macroscopic site. Then a model we satisfy a monogamy relation for a Bell inequality if and only if the macroscopic average correlations that we looked about satisfy the same Bell inequality. So in particular, if the quotient scenario is acyclic, then any no-signaling empirical model defined on the original big scenario will be monogamous with respect to all Bell inequalities. And moreover, for any no-signaling empirical model that we start with, then the macroscopic average behavior is known. So in particular, we prove that this is the case for multipartite Bell-type scenarios, provided the number of parties being identified as belonging to each macroscopic site. So the number of microscopic parties in each of these macroscopic sites is large enough, or is larger, so it's larger than the number of measurement settings that's available at each of these sites. So our approach highlights the reason that why monogamy relation for general multipartite Bell inequalities follow from the no-signaling condition, because this Barbosa theorem, this acyclicity thing, works for any no-signaling probabilities, doesn't depend on quantum mechanics at all. And so this approach sort of gives a structural reason why this result holds. And moreover, so in particular this result we show generalizes both papers that I mentioned in the beginning. So Pavlovsky and Bruckner have shown that monogamy follows from no-signaling for bipartite Bell inequalities, and we generalize this to multipartite Bell inequalities. And Ramanathan et al. Proved that the sort of macroscopic averages are local, but their proof was dependent on quantum mechanics, and they used so it's specific to quantum mechanical models. And in our proof, we sort of get rid of these and we just talk about no signaling, and we use this sort of structural explanation that depending on this theorem of Robin, which depends only on the structure of the compatibility between measurements. And then the approach is not restricted to multipartite Bell-type scenarios. So in general, more generally, we could apply the same ideas to get monogamy relations for contextuality inequalities, or to talk about macroscopic averages in contextuality scenarios. Not on this yet.
Thank you very much. Any questions? Yes?
Yes.
Very good results. Question:
So the which
general setting is
so you mean in particular the Brogan theorem or so yeah, so as long as you can do some sort of gluing thing, so the idea is you have so if you have, say you had so three random variables A, B, and C, and you had some sort of probability distribution over A, B, and another over B and C.
So this is a true theorem in the language that sense.
Yeah, so I mean, you can think, for example, of, yeah, you can think of like possibilistic probabilities, and it's just a natural join databases. You can think, I mean, distributions of over any semi-filled do that as well. So there's a number of examples. So there's this work by Tobias Ritz and Cecilia Flori, where they talk about leaves, which are basically sheaves where they have this gluing condition. And these are particular examples of those. But in a way, so the idea is if you have something on AB and something on AC, then you should, and they're compatible on B, there should be a map of these sort of compatible distributions, which is sort of a fallback to the global distribution. It's sort of the gluing thing. So distributions on AB. So if you have a distribution at AB, a distribution at BC, and they agree on the intersection of the marshals, then there should be a map that gives you a distribution on the three of them, which also marshalizes to two original distributions. So whenever you have these, then these resolve by Baronic goes through. As long as you finish up the other stuff.
Okay, very good. It's 12 o'clock. A quick question?
Okay, I have a quick question, sorry. Actually, Memorandum and what wrote all of paper on this sort which extends sort of this no signal. So we write monogamy relation based on say, this no disturbance condition.
Yeah.
Yeah. So Memorandum extend this result to contextuality by extending no signal to zero disturbance.
Yeah. So.
Yeah.
I
was wondering
so
how this scenario is different from this.
well, no disturbance is basically this thing, isn't it? And so in the last paper by Ramanathan, so I think they consider a very specific example of a particular case of contextuality inequality. So here we sort of this is more general results. As far as I know, but I'm not sure.
Okay, let's